Hi everyone, and today we are going to continue our discussion of improper integrals. However, today's example will be a bit different because in the previous examples we either dealt with even functions or let's say even functions with 0 to infinity integral, but today we are going to see an example where the function itself is neither even nor odd. So let's try to do that. So the example that we are going to consider is something like this. Integration from 0 to infinity dx x cube plus a cube, where a is greater than 0. So if you look at this integral, you can easily see that the function itself, if you call it f of x, is just 1 by x cube plus a cube, and this is neither even nor odd, because instead of x, if you put minus x, this will just pick up 1 minus sign over here, and that doesn't resemble in any way the properties that we saw for even and odd functions. So how to do this integral? Obviously we cannot use the trick that we used earlier, where we put a minus infinity instead of 0 and multiply by a half, because those tricks only work for even functions. So we cannot use a contour like this, that is the semicircular contour that we are used to. Rather, here the main idea will be to find the appropriate contour itself. So to do this integral, the first thing we are going to look at is something called a symmetry. So this symmetry means, if you notice that if you have this x over here, and if you multiply this with 2 pi I by 3, and if you take the whole root, that is not root, to the power cube of this whole thing, this will just return x cube itself, right? So if I consider a line on the complex plane that is parameterized like this, along that line the function itself will preserve the form it has in the integrand. So let me show you what type of contour that we're going to consider, and this is coming from this symmetry property. So since the contour is from 0 to infinity, that is the limits of the integration are from 0 to infinity, we're going to consider a contour like this. We'll start from this point, we will go, let's say, up to this radius r or distance r, then we'll try to build another arc of a semicircle or a circle, whatever you want to call it. However, since this symmetry comes at an angle 2 pi by 3, so we are going to enclose the contour like this, where this angle over here is just 2 pi by 3, and this is that line where this parameterization is valid. So let's give this line some name. Let's say this is from 0 to r, that is something you know. Let's call this c of r, and let's call this c of x, and we will go from 0 to r, then from this r to this point over here, let's call this point b, and finally we will get back to this point. This is our contour for this integral, and now we just have to use the residue theorem, and after using that we will proceed as before, where we need to break down the integral along these lines. So let's do that. So the first thing we are going to do is that we're going to use the residue theorem. So the residue theorem tells us that this integral along this closed contour will be the 2 pi I and sum of the residues, right? And to find the residues, you need to find the points where this function is singular, or let's say you want to find the poles or the singularities. And you can see that this z cube plus a cube, they will have one of the poles inside this contour. Let's call this is the point, and this x is our pole, and it will come from the equation z cube plus a cube equals to 0. That means z cube is equals to minus a cube. And now you just have to find the cube root of a cube itself. You will have 3 points, and one of them will reside into this contour, or let's say this region. And if you calculate the root, you will see that the residue is simply sorry, not the residue, the pole itself. The pole occurs at z equals to a e to the power I pi by 3. This is just coming from this calculation of the cube root of minus a cube, and only one of the pole is inside this contour, so, or let's say inside this region bounded by the contours. So this is the point of interest. For this point we have to calculate the residue. So now we move forward to calculate the residue. So the residue at point a e to the power I pi by 3, you can easily do it by differentiating this stuff, or you can use the method that you saw in the first video. I'm gonna go with the second one because that's way easier. So the residue at this point is simply this 1 upon 3 z square, where you have to put z is equals to a e to the power I pi by 3. If you do that, this will turn out to be simply 1 upon 3s square e to the power minus 2 pi I by 3. This is our residue, right? So we have this dz by z cube plus a cube as 2 pi I divided by 3 a squared e to the power minus 2 pi I by 3. Now one part is done, and the next part is to break down this integral along these contours. So let's do that. If you break it down just like you saw in the other videos, it will be first, it will run from 0 to r. Sorry, the infinity limit has to be taken later. So along that line, z is just x because the imaginary part is 0. You will have this. Then along CR, that is this semicircular arc, and we keep it as dz z cube a cube. And finally along the CX line, that is this one, CX. And note that this arc has a radius of capital R, right? And this point denotes this capital R e to the power I 2 pi by 3. That's the point on the complex plane. So since we are doing an integration, and obviously we are coming from b to 0, we are going to mark this radius as a variable itself. That is the let's say you are coming from here to here, then from here to here, and so on, and this radius will change, and it will start from r and it will end up to 0. So instead of using capital R, let us use small r so that we don't get confused. So you are starting from small r, which is equals to actually capital R, and you are finally ending up at point 0. So these are the limits. And along this line, instead of capital R, use small r so that you don't get confused that it is indeed a variable. At any point, not just this one. Let's say you want to take this point, this can also be written as r e to the power, let's say r prime, because this, when you are at point B, this small r will be capital R. However, when you are, let's say this point, let's say y, here the value of r will be different, so that's why I'm using the small r prime, and this will be to the power I 2 pi by 3, right? Something like this. And since you are running from b to 0, that's why you have to keep this variable form. So this will simply tell us that along that CX line, any parameter, let's say our value z, not the value, sorry, the complex variable z is just r e to the power 2 pi I by 3. So this means dz is equals to dr e to the power 2 pi I by 3, like this, right? Okay, so let's put these things on this integral and write it over here. So this will just be dr e to the power 2 pi I by 3, and we'll have this r e to the power 2 pi I by 3 whole cube plus a cube, right? Now we need to simplify all these stuffs. So again, write them down. Now if you notice that this smaller is just a dummy variable, right? So instead of r, you can also write it as x. So let's do that. And obviously what I'm going to do right now is that I'm going to flip this to r and 0, and I'll pick up a minus sign over here. So if you do that and write the terms explicitly, this will just be minus r0. Instead of r, now we're putting x because that's just a dummy variable or the integration variable. And there is this e to the power 2 pi I by 3. Now notice the fact that this and this, they will make a useful combination. That means they're the same thing. So if you just factor this integral out, you will have something like this in the next line, 1 minus e to the power 2 pi I by 3, which is a constant, and there is this integration of 0 to r dx x cube plus a cube plus c of r dz z cube plus a cube. So we are almost done. Now we need to take the limit. Take the limit r goes to infinity, because our original integral ranged from 0 to infinity. And let's say this is our equation number 1 into 1. So if you do that, obviously you can see this part, the first part over here, the limit will change from 0 to infinity, and all you need to do is to figure out what happens to this CR piece, that is the piece coming from the semicircular arc. And if you have followed the previous videos quite carefully, you can already see that this part will be 0, because the upper polynomial is just 1, which is a constant, and the lower polynomial, or let's say the lower function, has a degree of 3. So this will be 0 when you take this limit r goes to infinity. Or obviously you can check it using the maximum modulus principle that you guys saw in the other video. So I'm not going to do that because this can be done mentally. There is no need for this explicit calculation. And finally you need to equate these two parts, that is coming from here and from here, because these are the same thing, right? I just broke down the contour integral into the parametric integrals. So finally we will have 1 minus e to the power 2 pi I by 3. There is this integral from 0 to infinity dx x cube plus a cube is equals to 2 pi I 3a square e to the power minus 2 pi I by 3. Now you just need to divide this whole thing by this guy and simplify. So 2 pi I like this, there is this 3a square, and you'll have 1 minus e to the power 2 pi I by 3, and there is this e to the power minus 2 pi I by 3. Now you take this e to the power 2 pi I by 3 down, you multiply them, and you use the Euler's identity to simplify all these things, and you'll finally have the result in terms of real numbers, and there will be no imaginary parts. So this will just be pi divided by 3a square sine pi by 3, and if you use the numerical value of sine pi by 3, this will just be 2 pi by 3 root over 3 a squared, and this is your answer. So the calculation procedure is not that difficult. The only difficult, or let's say the conceptually deep part, is to choosing the contour. You can say that why didn't I choose a contour that's like this, that didn't even contain any singularities, because in that case that would be just 0, right? And it's not a valid contour. It doesn't mean you are going from 0 to infinity and all that stuff. So a general rule of thumb, if you see functions like this, would be to multiply the variable that is like this over here. You see this x cube, that's why I multiplied it with e to the power 2 pi I divided by 3, and if you cube it, that's just the same thing, right? And let's say if you have something like this, dx by x to the power n plus whatever, something like this. So the integration limit from 0 to infinity, and you have something like this. So in this case, the contour would be something like this, that will come from this equality, that is x to the power x times e to the power 2 pi I by n to the power n is just x to the power n itself. So in that case, the contour will look something like this. It will start from here, that is from this 0 point. You have the semicircular arc, and you need to make sure that it contains one of the singularities. That's the whole reason of this parameterization. There might be 1, there might be 2, and there might be finite amount of singularities that is coming from demanding the denominator to be 0. And this contour will have an angle, that is, let's say this is point A and this is point B. This OB will be parameterized via r e to the power 2 pi I by n. This is a general trick that you can use whenever you are encountered with integrals like 0 to infinity and the function itself is neither even nor odd. And the rest of the calculation, you can just use the previous ideas, that is breaking down the integral, calculating the residue, finding the singularities and all that. If you combine all of those things, you can easily evaluate this kind of integrals. So this will be it for today, and I'll see you guys on the next lecture. Thank you.